have your last section of notes pulled up for Chapter 2. So this is going to be Section 2.6. And there's quite a bit of stuff in this section. There's quite a bit of stuff that you're going to need to memorize for this section. So for those of you, and I get this every year, I get like, well, I'm just not good at math. Okay, you don't have to be good at math. You just have to memorize some stuff. Surely, I can get you all to memorize some stuff. So we're going to be looking at some like really weird graphs that have holes in them or asymptotes. And so, you know, whenever you say, when I ask you like, hey, what's the domain of a function? And if you see like a denominator and you're like, ooh, I see a denominator. X can't be 2. You know, you've told me a domain like that before. Oh, everything but 2. X can't be 2. Well, why not? Why can't X be 2? What happens when X is 2? And some people come back and say, well, you told us that it blows up at 2. Well, yeah, but specifically on a graph, what does that look like? I mean, really, do you see a little explosion at 2? No. You see something weird on a graph. It's not a... We're going to look at what does happen when what I call your denominator blows up. So we're specifically going to be looking at rational functions. Rational functions have a numerator and a denominator. Easy. It's a rational function. So, in order to see what's going on at some really weird x values, the first thing you have to do is you have to make sure that that numerator and denominator that we're looking at, numerator, denominator, they have to be factored. So you have to make sure that everything that we're looking at is in factored form. Once we get it in factored form, we're going to see what x's cause my denominator to blow up. What x's make my denominator equal 0? Does that x make my numerator 0 also? And if it does, there is a hole in your graph. Like you'll be just drawing your graph and you have to be like, oh, stop. Put a hole there. Okay, now keep it going. Okay? That's one thing that might happen on an actual graph when your function blows up, when your denominator is 0. Just check to see, does that x value cause your numerator to be 0 also? So, I went ahead and took our first function. I factored the denominator. The numerator was a prime linear factor. I couldn't factor that anymore. Factored our denominator. And check this out. If I asked you, what's the domain? You would tell me, x can't be negative 2. X can't be positive 2. Good job. You are totally correct. Now, why not? Why can't they? What happens? Specifically, what happens? So, let's check out negative 2. Do you see that when x is negative 2, this blue cloud equals 0? And 0 times anything is 0. So my denominator is definitely wiped out when x is negative 2. What about my numerator? When x is negative 2, is it 0? Yeah. So when there's an x value, like negative 2, that makes your denominator and your numerator 0, we say there's a hole in the graph at that spot. Yeah, I know. The function blows up at negative 2. Okay, but what does that look like on a graph? There's an open circle there. Not filled in. Open circle. If it were filled in, it would all be okay. It's not okay. There's an open circle. There's a hole at x equals negative 2. Next one. Notice I'm looking at this function named g, has to be in factored form. So the denominator is fine. The numerator I had to factor. If I asked you all, hey, what's the domain? You'd be like, oh, x can't be negative 3. Correct. Why not? Because if x were negative 3, my denominator would be 0. And my numerator would be 0. There's a hole at negative 3. There's a hole in my graph. There's an open circle when x is negative 3. There's nothing filled in at negative 3. There is no ordered pair called -3 comma. Doesn't exist. There's nothing there. All right, and then what you're going to see on this page is like shortcuts. So what I'm telling you is the number that makes your denominator and your numerator equal 0. Here's how most of you are going to memorize it. When you see the same factor in the top and the bottom, there's a hole there. That's okay. You can memorize it that way. When you see the same factor in the top and the bottom, there's a hole there. Well, not there, but there's a hole at what would make that factor be 0. Now, what happens when there's a number that makes your denominator 0, but it doesn't make your numerator 0? There's a number that does make your denominator 0, but it doesn't make your numerator 0. What happens then? It blows up. I know it blows up. Like specifically on a graph, what does it look like? There's a vertical asymptote there. You have a vertical asymptote. So you have a dotted vertical line, your function like slides up to it and then never touches it. Vertical asymptote. There is no filled in point right there. Your function won't cross that vertical asymptote. It won't touch it. It cannot occur. No point can occur at that location. So let me show you a couple of these. I took the function. I went ahead and factored the denominator. And then I could ask you, hey, what's the bit domain? You would say x can't be 3. And I'd say, I know. Good. Why? What happens? If x is 3, this blue cloud becomes 0. Your denominator is 0, okay? If x is 3. If x is 3, what's the numerator? Not 0. So you see how the number 3 causes this to be 0, but it doesn't cause this to be 0? There's a vertical asymptote at x equals 3. Next one. Got to get it in factored form. You have to look at it in factored form. So, yeah, there are two numbers here that cause your function to blow up. There are two numbers that are not in your domain, positive 2 and negative 2. Why not? What happens there? Well, at negative 2, when x is negative 2, this blue cloud is 0. Wipes out my denominator. Numerator is still 10. So when x is negative 2, there's a vertical asymptote at x equals negative 2. At positive 2, this blue cloud is 0. Wipes out your denominator, but the numerator is still 10. So when x equals positive 2, there's a vertical asymptote there as well. Wait, what? How can you have two vertical asymptotes? I'll show you in a little bit. Last one. The top is a prime linear factor. I couldn't factor it anymore. The bottom one could totally be factored, so I did. What's the domain? You're going to tell me, well, x can't be negative 5 and x can't be negative 1. Why not? Because when x is negative 1, there's a vertical asymptote. See? Here but not here. There's a vertical asymptote. When x is negative 5, there's a hole in the graph. Yep, you can have both. You have a vertical asymptote at one of the places that makes your function blow up, and you can have a hole at the other place that makes your function blow up. Alrighty, now that's vertical asymptotes and holes. Let's talk horizontal asymptotes and holes. Again, we're still looking at rational functions. So we're still going to have a numerator and a denominator. Something else you got to memorize. Horizontal asymptotes. So like a dotted line like this. where your function's going to zoom up to it, but never touch it. Okay? Horizontal asymptote. So if you got to look at degrees in your numerator and denominator. If your denominator degree is larger, let's say your denominator degree is larger. Let's say you've got a quadratic over a cubic. Your denominator degree is larger. You're going to have a horizontal asymptote at y equals 0. If your denominator degree is larger, let's say you have a linear over a quartic. Your denominator degree is larger. You're going to have a horizontal asymptote at y equals 0. Next case. What if your degrees are, let's do the next one. What if your numerator is bigger? What if your numerator degree is bigger? What if you've got a quartic over a quadratic? Quartic on top, quadratic on the bottom. Your numerator degree is bigger. There is no horizontal asymptote. Your function won't level off. What if your degrees are equal? Okay. What if you've got a quadratic on top and a quadratic on the bottom? Degrees are equal. There's going to be a horizontal asymptote. Your function will level off. Where? Make a fraction out of your leading coefficients. So get your leading coefficient from the numerator, get your leading coefficient from the denominator, make a fraction out of them. And say, my horizontal asymptote is going to be at y equals that fraction. Okay, let's try some. Number 1, the degree of the denominator is 1. I'm going to start here because I think that's easy for you all to see. The degree of the denominator is 1. What's the degree of the numerator? Well, there is no x there. Or if there were, it would have to be x to the 0. So its degree is 0. So you can see that this falls in case number 1. My denominator degree is bigger. Answer, I've got a horizontal asymptote at y equals 0. Number 2, quadratic, quadratic, same degree. Up at the top, case number 2, degrees are the same. You will have a horizontal asymptote. Where? Y equals 5 over 1. You're going to have a horizontal asymptote at y equals leading coefficient over leading coefficient. Last example. Numerator degree is 2, denominator degree is 1. This is case 3. There is no horizontal asymptote. That's just the answer. There is no horizontal asymptote. Okay, now, slant asymptotes. Slant asymptotes are a special case of case number 3. So let me, case number 3, slant asymptotes. Only if 1 degree higher. Okay, so there can exist such a thing as a slant asymptote. So it's just a slanted line, okay? It's a slanted line, and it holds in your function. So your function might kind of do this up against your slant asymptote. They're not common. And it occurs only in case number 3, but then only when you're 1 degree apart. So, yep, this is case number 3. I'm 1 degree apart. This would be a case where I would have a slant asymptote. However, if this were a cubic and a linear, I wouldn't have a slant asymptote because I'm not 1 degree apart. Okay? So, can see, number one, I've shown the degrees. There would be a slant asymptote. I'll tell you how to find it in a minute. Check out the degrees. They're not just one apart. There's no slant asymptote. In fact, there's no slant asymptote. There's also no horizontal asymptote. Because remember, this is just a special case for horizontal asymptotes, or for case 3. And then, yep, our degrees are 1 off, so you're going to have a slant asymptote. Now, here's how to find it. Think about this. A slant asymptote is just a slanted line. You all know what equations of vertical lines look like, x equals. You know what equations of horizontal lines look like, y equals. What do equations of slanted lines look like? Y equals mx plus b. Let me show you how to find your mx plus b. Okay? It's not hard. You're not going to like it, but it's not hard. So, you're going to use division to find equations of your slant asymptotes. And remember, they can only be 1 degree apart. So, check this out. I took my numerator and my denominator, and I divided them. I took the smaller degree into the larger degree, okay? And I did this one by long division. So I could have, this is a linear factor with a leading coefficient of 1. I totally could have used synthetic, and I will in a minute. But I used long division. So I got this. I got x plus 6, and look, I had a remainder. That's okay. We're going to ignore the remainder. This is my slant asymptote line, mx plus b. Y equals mx plus b. That's my slant asymptote. Let's see, where else did I have a slant asymptote? Number 3. I think since this is a linear factor with a leading coefficient of 1, I'm going to show you. Let's do our division using synthetic division. So let's grab our coefficients and let's send positive 2 through. Make sense? This would be a factor. I'm dividing by x minus 2, so I'm going to send my 0 through it. Well, what I think might be a 0. So I send 2 through synthetic division. Oh, I did get a remainder. That's not a 0. I did get a remainder. Ignore it. Here's your mx plus b. Here's your mx plus b. That's your slant asymptote. Okay, we're almost there. Putting it all together, on this last page of notes, I am going to, let's use everything that not everything, let's use some of the things that we've learned. Let's graph a rational function. Oh, it's going to be crazy what it looks like. It's going to be so cool. We're going to graph this, but before we graph it, we're going to write down pretty much everything we know about it. So, domain. Look at the domain. Tell me what x can't be. X can't be 4, right? Cool. X can't be 4. X can't be 4, or in interval notation, negative infinity to here, stop, don't include it, pick up here where you left off, and go to infinity. Now, I wonder why x can't be negative 4. I wonder what happens at negative 4. Is there a hole? Well, do you see x plus 4 up here? Does negative 4 cause your numerator to be 0 also? No. No holes. How about a vertical asymptote? Oh yeah, that's what's going on. That's why your domain can't include negative 4, because there's a vertical asymptote there. So you can see negative 4 causes this to be 0, but not this to be 0. So we got a vertical asymptote when x is negative 4. How about horizontal asymptotes? Well, my degree is the same. I'm going to have a horizontal asymptote. where y equals 5/1. Y-intercept, plug 0 in for x. There you go. It's going to cross the y-axis at -3/4. X-intercept, plug 0 in for y. Honestly, I don't remember if we've talked about this or not, but how does a fraction equal 0? Is it when the denominator is 0? Oh, no. No, not when the denominator is 0. Right? The function blows up when the denominator is 0. How does the function equal 0? When your numerator does. When your numerator is 0, 0 divided by anything is 0. So how do you make this work? Just focus on your numerator. Focus on your numerator. Get your numerator to be 0. Then your fraction is 0, right? Get your numerator to be 0. Then your fraction is equal to 0. So focus on the numerator only. Solved it. X equals 3/5. That's my x-intercept. So here's what I'm going to do. I'm going to take all that information. I'm going to come over here to my graph. Let's see. I think the first thing I'm going to do, I'm going to put a vertical asymptote at x equals -4. Here I go. You with me? -4. 1, 2, 3, 4. Vertical asymptote. There I go. What next? Ooh, horizontal asymptote, y equals 5. Let's draw it. Horizontal asymptote, 1, 2, 3, 4, 5. Freaky. We have a y-intercept at -3/4, so like here-ish, y-intercept at -3/4, right? X-intercept at +3/5, so here-ish somewhere. What on earth does this graph look like? So have I graphed everything I can? There's nothing to graph. I mean, like, there is something to graph here. I graphed a vertical asymptote there, but these go together. There was no hole. There's a vertical asymptote. I got my intercepts. Let's see what it looks like. So now, this is when I'm going to go to my graphing calculator. Let me switch to my graphing calculator on my screen. Okay. I don't know if you knew this or not. I've typed in a couple of functions, but I turned this equal sign off. So we're not going to see my y2. We're only going to see my y1. Now, warning, when you type in 5x minus 3 on the top and x plus 4 on the bottom, if you don't tell your calculator specifically, this is my numerator, this is my denominator, it's going to do order of operations not the way you want it to. So make sure, put your binomial in parentheses, and then hit graph. Whoa, I feel like I'm missing something. I'm going to zoom out a bit. Zoom out is option 3. Oh, yeah. Okay, so here's what your calculator doesn't show you. Your calculator doesn't show you any holes in your graph. It doesn't draw asymptotes for you. You can see that it does cross the y-axis right here, really close to the origin. We already knew that. It crosses the x-axis really close to the origin. We already knew that. But now you see where to draw the pieces of your graph. You've got a graph that's in 2 different pieces. So you're going to draw a boomerang type thing in the upper left corner of your graph. Careful, don't cross your asymptotes. And in the bottom right corner of your graph. Careful, don't cross your asymptotes. Here's what I mean by that. going to draw our boomerang-shaped pieces in the upper left corner of our graph. And then, okay, see how it was bounded by my red asymptotes? And then using this bottom corner right here, not quadrant 4, it's not what I'm talking about. I'm talking about the ones bounded by my asymptotes. I'm going to try to come up here near this one, come up near this one, hit that intercept, and head up toward that one. Hit it, head up toward that one. That's what the graph looks like. So all this I did without a calculator. The only thing I used my calculator for was to see where to draw the pieces, because now I've got my graph divided into all these sections, and you need to know where the pieces go. Let's do one more really quick. I'll do the last one. So notice what I did. I first factored it, okay? What's the domain? Well, x can't be 0. X can't be negative 5 halves. Can't be 0. I didn't write it as interval notation, okay? Why can't it be those two numbers? What happens there? Well, let's find out. Is there a hole? No, because I don't see this factor up there, and I don't see this factor up there. Or, how about this? 0 would make my denominator 0. Nothing's going to turn that number into a 0. Negative 5 halves makes my denominator 0. Nothing's going to turn that number into a 0. So there are no holes in the graph. There are vertical asymptotes at 0 and negative 5 halves. Vertical asymptotes, because those two numbers would make the denominator 0, but not the numerator. Horizontal asymptotes. Well, my denominator degree is bigger than my numerator degree. I think that is called case 1. We're going to have a horizontal asymptote at y equals 0. Let's find my intercepts. This is funny. Plug 0 in for x. Some of you mathy people are like, you can't plug 0 in for x, Miss Neal. We just determined x can't be 0. Other of you are like, okay, I'll plug 0 in for x, and you plug 0 in for x, and all of a sudden, boom, oh shoot, you just blew up. That means there's no x-intercept. Hold on. That means there's no y-intercept, right? Yeah, right. When I plug 0 in for x, there's no y-intercept. Oh, I wonder what I did down here. Yep, same thing. X-intercept. So what happens when you plug 0 in for y? Do you remember? How do you make a fraction be 0? How do you make a fraction 0? Well, you certainly don't want your denominator to be 0. You want your numerator to be 0, okay? So here we go. Ready? Let's just focus on the numerator. Let's write 0 equals... No. 0 can't equal negative 3. So there's no x-intercept. I tried plugging 0 in for x to get y. There wasn't one. I tried plugging 0 in for y to get my x-intercept. There wasn't one. This graph is not going to cross either axis. So what on earth is it going to look like? Well, let's get some of these asymptotes drawn. You can make your scale pretty big. All right, so I have a vertical asymptote at 0. And at negative 5 halves, negative 1, negative 2, right here. And a horizontal asymptote at y equals 0, okay. never going to cross the x-axis, never going to cross the y-axis. Got my asymptotes drawn, so what on earth does this thing look like? I am going to turn equation number 1 off, and I'm going to turn equation number 2 on. I've already got it typed in. Here's what it's going to look like. I thought I turned them off. Did I not turn them off? I didn't turn them off. There we go. Whoa, what? I've got asymptotes there. Hold on a minute. Let me zoom in a bit. Because remember I zoomed out? Ooh, that's cool. So, basically, on your paper, you've got basically 6 portions. Our asymptotes divided our paper, our graph into 6 portions. In the bottom left portion, you've got like a boomerang type piece here. In the bottom right portion, you've got a boomerang type piece here. And in the upper middle, you've got a parabola looking thing. So boomerang looking down here, boomerang looking down here, parabola looking up here. Okay, and just a real quick what if. We're pretty much finished, but what if? What happens if you have a hole in your graph? How do you do that? Your calculator's not going to show. Okay, pick a number, any number. How about 2? What if there were a hole at x equals 2? If there were a hole at x equals 2, I've already got my graph drawn. Here's what I would do. I would find where x is 2. I would go to my function, erase it, and put an open circle there. Go to 2, erase it, and put an open circle there. If there were a hole at x equals 2, I'm going to go find the function wherever it is, right there. Erase it, put an open circle there. Okay, that's how you would draw. I never showed you in either of these examples, but that's how you would do it. Now I'm going to take that away because there's really not a hole there. That was just a what if. All right, good luck.